Hello, everyone. Welcome to the VaNTAGE seminar. Please feel free to come into the room. Great. Well, today in the VaNTAGE seminar, we're continuing our series on fundamental groups of curves and their arithmetic applications. And today we're very happy to have Chris Rasmussen, who will be talking about heavenly elliptic curves over quadratic fields. And Chris, is it all right if we record this talk?
Yes.
Great, great. Well, and please feel free to ask questions. Great. Go ahead, Chris.
Okay, thank you. Yes, I'll reiterate that. I'm very happy to receive questions at any time. And I'm also delighted to receive this invitation to speak in VaNTAGE. And I'm very happy to share some ongoing work with Cam McLean at the University of Michigan Flint. So maybe I can just start with a little bit of an introduction of what I'm hoping to do in this talk. So I'll first give an explanation as to what I mean when I talk about a heavenly abelian variety and why we might care about them. I'll give a survey of some older finiteness results and a new finiteness result that Cam and I have established in the last year. And this new result contrasts from the style of the old results, where a field of definition was fixed and we let a special prime of bad reduction vary, and we're sort of swapping those roles. So we consider what sort of finiteness results might be possible if we fix one prime and let the field of definition for an abelian variety vary in some controlled fashion. So we actually established some new finiteness results in that direction. And along the way, we discovered that there's a striking similarity between the behavior of these heavenly elliptic curves and elliptic curves that have complex multiplication in terms of the behavior of the traces of Frobenius elements. And I'll explain that a little bit more in detail when we get there. And this allowed us to actually give a characterization of heavenly elliptic curves among those that have complex multiplication. And I'll report, if there's time, on a little bit of computational results we obtained as well. So let's just start this story by considering the following tower. I have a number field K, and I pick one rational prime. I'm going to assume L is odd for convenience. Almost everything I say is true when L is equal to 2 with mild variations, and I just prefer not to go into all the mild variations. We can mimic the algebraic extension k bar over k by looking at the function field extension k bar of t over k of t. The Galois group there, of course, the absolute Galois group of the number field k. And then atop k bar of t, we can look at the maximal extension obtained by only allowing ramification at the places corresponding to t equals 0, 1, and infinity. And then intermediate there, we have a maximal pro-L extension of k bar of t. And I'm carving out the Galois groups for these extensions. Every single extension in this picture is Galois. And of course, by standard ideas, this leads to a short exact sequence among the various Galois groups where the sort of geometric fundamental group pi bar sits as a normal subgroup inside of the fundamental group pi. And the quotient is exactly giving us the absolute Galois group of k. So we have this connection between the geometric and arithmetic information available to us inside of this tower. And there's a standard recipe given any short exact sequence of groups that yields a representation. And the recipe is as follows. If you have an element inside of GK, we can lift it up to the center group pi, where it may act as conjugation. And anything inside of pi bar, of course, pi bar being normal inside of pi, is going to be sent back into pi bar. And this gives us an automorphism of pi bar, but only up to an inner automorphism, since, of course, there's not a uniqueness result regarding the way we choose the lifts. That action I just described gives us a map from GK to the outer automorphisms of pi bar, and we can factor through the appropriate characteristic normal subgroup to get the outer automorphisms of the pro-L version. Right? And from a geometric perspective, this extension is just cataloging and studying all of the coverings of the projective line that branch only over the 3.01 infinity. All right. So Ahar asked a question related to this representation. So that representation I defined on the previous page is not injective. It cuts out via its kernel a fixed field, which I'm going to denote yama. And Ahar demonstrated in the 80s that yama is naturally sitting inside of this possibly larger field 10, which is purely arithmetic in its definition. So the definition for 10 is it's simply the maximal pro-L extension we can build over the cyclotomic L tower of K that stays unramified outside of L. And it was a result of Ohara together with some work with Anderson that demonstrated that Yamas definitely sits inside of the field 10 in all circumstances. And he asked, both originally in his 86 complex multiplication annals paper, but also in several other locations, whether or not these two fields actually coincide. And just to explain the choice of notation, the character Yama here is the kanji representing mountain, and the character 10 is the kanji representing heavens. And so we're asking whether or not this natural geometric extension actually reaches all the way up to the natural arithmetic extension given by 10. And so one way to think about this problem is we're asking, does the mountain reach the heavens? We definitely have this containment of Yama inside of 10. We're wondering whether or not there's an equality. And this is partially resolved. So this is a theorem of Francis Brown by way of a result, an older result of Romyar Sharifi. Brown resolved the Delina-Hara conjecture affirmatively, and Sharif had previously shown that if L is an odd regular prime, then the equivalence of these two fields is precisely equivalent to this conjecture of Deline and O'Hara. There are some natural subfields of Yama running around given from arising from geometry, excuse me. The point is if you have a smooth projective curve that covers P1 minus 3 points in a pro-L way, that is, I want it to branch only over 0, 1, infinity, and I insist the Galois closure of this covering has L power degree, then it's a theorem of Anderson and O'Hara that the Jacobian of such a curve will have L power torsion that generates a subextension of Yama. And so if one is interested in understanding this field Yama, there's a natural source of large subextensions, provided you can find curves inside of the pro-L tower over P1 minus 3 points. Unfortunately, it's not so easy, especially if you bound the degree of such maps. It's very hard to find examples in practice. There are a few standard families like Fermat curves of L power degree, Heisenberg curves, certain towers of modular curves, but sort of beyond the natural sources of examples, these are very rare to see in practice. And so to both understand why these are so rare and also to return to O'Hara's question and understand what distinction, if any, there is to be made between 10 and Yama, we're going to ask about a slightly more general object. That is, we'll just ask from an arithmetic perspective, what are the abelian varieties that have L power torsion sitting inside of 10, right? This is a weaker condition possibly than sitting inside of Yama, but certainly if we can describe these varieties, we would have a toehold on trying to understand exactly which ones satisfy the possibly more stringent containment inside of Yama. Okay. And this motivates the definition for calling something a heavenly abelian variety. It's precisely this containment condition. If the L power torsion of the abelian variety generates a subextension of this field 10, remember the maximal pro-L extension of the cyclotomic L tower unramified outside of L, then we'll call that abelian variety heavenly, technically heavenly at L over the field K. And we're going to be interested in questions about finiteness. And so I'm going to define a couple sets here. HKGL will simply track up to K isomorphism. Abelian varieties, which are defined over K, have dimension G and have this heavenly at L property. But of course, you can ask the question of heavenliness at any particular prime. So we'll also consider the following set, which you can sort of think as a subset of a fibered product between abelian varieties and rational prime numbers, where we simply take pairs where the pair consists of an isomorphism class of an abelian variety and a rational prime L. And the condition is that A happens to be heavenly at L over K. And the condition of being heavenly is extremely strong. It has two immediate consequences to the structure of the field generated by the L power torsion. The first, of course, is that this field extension has to be unramified away from L, and that immediately dictates a lot of arithmetic information, right? There's only, the second thing is that we have this extension that must be pro-L. We can consider what these two pieces of information tell us. First of all, the unramified behavior of the extension guarantees that we have good reduction outside of the prime L. So this is already an extremely strong condition to place on an abelian variety. In particular, once you fix the field of definition and the dimension and the prime at which you want to be heavenly, there can only be finally many isomorphism classes under consideration. This is essentially a consequence of the Shafarevich conjecture. Although it's slightly delicate, we need the unpolarized version of the Shafarevich conjecture. So the Shafarevich conjecture was originally resolved by Faltings, and then shortly thereafter, Sarin proved an unpolarized version of this result, which basically guarantees that if you fix the dimension and the field of definition, the reduction type of the abelian variety limits you to a finite number of isomorphism classes. And so this is an even more stringent condition, so the finiteness is also available. On the other hand, we also have the fact that this extension over an L root of unity, really L infinity, but the L through unity and L power infinity, these are both going to be pro-L extensions as well. So this extension needs to be pro-L. And that's actually a very mild condition because most of the pro-L-ness of this extension we get absolutely for free, right? If you start at the L torsion and adjoin the L power torsion, this is already always giving you a pro-L extension for any abelian variety. And so all we really care about is that the very first step from K mu L, guaranteed to sit inside of the L torsion field by the existence of the V pairing, sitting inside of KAL, we just need that to be an L power extension. And I'll just mention in the specific case of elliptic curves, which I'm going to specialize to often throughout this talk, this is even more stringent because the shape of the Galois representation into GL2FL only allows for two possibilities. Either this is a completely trivial extension if you want it to be heavenly, or it has order exactly. So what else can we say? Let's talk about the structure we can elicit from knowing an abelian variety is heavenly. So let's take an abelian variety and suppose that it truly is heavenly at L. And I'll let chi denote the L-adic cyclotomic character of this abelian variety. Then it turns out the representation for the L torsion on such an abelian variety is highly constrained. This is essentially due to the nature of having the torsion group, which we can view as a finite vector space over FL, of course, inheriting this action from the representation that's constrained to be almost pro-L. This essentially leads you to show the existence of a Galois stable flag of subspaces inside of the torsion. And as a consequence, you get this very nice shape for the Galois representation. It's upper triangular with respect to a carefully chosen basis. And as you go down the diagonal, what you see are powers of the L-adic cyclotomic character, of course, all modulo L, since this is just the image over FL. Then we know some additional information, right? This is the Galois representation attached to an abelian variety. This should be chi to the G, right? My first typo, probably not even my first typo, but whatever. So the determinant of the representation here has to give the G's power of the cyclotomic character, which gives us the information that if we sum the entries on the diagonal, we will get not one, but G, excuse me. In the elliptic curve case, of course, this tells us that the two characters exponents will have to sum to one modulo L minus. And the G equals 1 case is especially strong because, of course, if you have a heavenly elliptic curve with this upper triangular shape, right, just this 2x2 block in the corner, then what you're really saying is that you've equipped the elliptic curve with an L rational isogeny over K. So K rational isogeny over L isogeny, which is rational over K, precisely because the first column of this representation cuts out the kernel of such an isogeny. When Akio Tamagawa and I first considered the distribution of heavenly abelian varieties long ago, we made the following conjecture, that if you fix the field definition K and the dimension G, but continue to allow L to vary, then we should still have only finitely many distinct classes of heavenly abelian varieties. And in particular, we can think of this as sort of a bound that past some constant, depending on K and G, but nothing else, primes larger than that constant cannot admit heavenly abelian varieties over that field in that dimension. And this is still an open problem, although there are several partial results that come in one of two flavors, roughly speaking. One is under an additional assumption or an additional specialization. It is possible to show the finiteness result. The other is that if we look at a natural occurring subclass of all heavenly abelian varieties, for example, having complex multiplication, having semi-stable reduction, things like this, it is possible to obtain finiteness results. And so this is a partial list of the available results. I just wanted to try and give a sampling here. Under the assumption of the generalized Riemann hypothesis, Akio and I were able to give a full proof of the conjecture. Ozeki was able to demonstrate that when the abelian variety is assumed to possess complex multiplication over its ground field, then this set is finite. And in slight generalization of this, first, my former PhD student, Abby Burdon, showed that elliptic curves with potential complex multiplication, so complex multiplication over any field, not necessarily K, will have a finite result available. And then David Lombardo was able to prove a few years later, a similar fineness result in all dimensions, not just dimension one. In specifying elliptic curves in dimension one and fields of definition of small degree over Q, we were able to establish finiteness unconditionally. This was through a careful study of the behavior of the special fiber on a heavenly abelian variety. And we were also able to obtain some uniformity results under the generalized Riemann hypothesis. So the results we have here don't apply in the case of degree even, but for odd degree, we actually get a uniformity result, meaning that given only that the degree of K is some fixed odd number, the bound on L depends just on G and not on the number field K itself. And I also want to mention that Abby's results were actually a little bit stronger than just finiteness in the case G equals 1. She also obtained a uniform result. So in terms of the degree of the extension over Q alone, the field of definition gives a uniform bound for admitting a heavenly elliptic curve with potential complex multiplication. And these two results that I've highlighted in red, I'm going to refer back to a little bit later in the talk because they provide some helpful constraints in describing a more general finiteness result. And
Chris?
again, I want to, please, yes.
Yeah, I'm just curious. Can you say maybe a few words about the role of GRH? Is this just for Chebytarov bound, or is there more to it?
It is essentially a Chebytarov bound. All of the arguments running through a lot of what I'm talking about, both old and new, involve trying to finagle a contradiction using the VaNTAGE bound. And you need a prime of small norm, and under GRH, it's much easier to find one. And so this is exactly what's going on. And in fact, this is a great question because here, why did we have to stop at degree 3? Well, we were just able to use a result of P.D. Elliott, right, saying that there's sublinear growth for the first least residue as long as the degree is less than 4. So there's a degree minus 1/4 showing up somewhere, and this is why we get degree 3, an argument that works, and beyond that, we're not able to extend it unconditionally. Yes. There are other places where we use GRH in a slightly different way, but it is always because a better bound from Chebytarov is available under GRH. Yeah.
Excellent. Thank you.
Yeah, thank you. Yeah, so I did just want to mention that there are several other results that I don't have time to mention in complete detail. Araya Momose considered a case of quaternionic multiplication. There are some generalizations, so sort of considering analogous versions of this conjecture in different contexts. And so I want to mention the work of Ministas and Okamura. And then Dasakar recently had a slight generalization as well, worth mentioning. Okay, so the results that Akio and I were able to establish previously and are sort of running through the results from the previous slide all involve fixing the field of definition, fixing the dimension, and then letting this prime L vary and asking, should we expect finitely many or infinitely many of these sorts of abelian varieties to exist? And now I'd like to discuss the problem where we exchange the roles of L and K. So now we will fix the prime L and ask about varying the number field K. Obviously, we need to be slightly more careful in terms of formulating this. I can't just let K vary unconditionally without any constraints. So let's consider why that might be. Here's one silly thing we have to be aware of. If I just take an elliptic curve that has good reduction away from 1 prime and base change up to its field of L torsion, then we're trivially heavenly and there's sort of no content here. So if I don't put some control on the number field K, there's no hope of getting a finiteness result, or at least extremely unlikely to obtain a finiteness result, because all I need now is to obtain good reduction over some extension. And then after a fine extension beyond that, I'm guaranteed to meet the heavenly condition. And so our solution there is to simply bound the degree of the field of definition K. So when we consider this perspective of fixing L letting K vary, it's not completely running over all number fields, but over some naturally chosen family of number fields, such as extensions of fixed degree over Q. In fact, we have more general results than just that. We can do what is standard in some areas to take any fixed field K naught and look at extensions of bounded degree above K naught, and analogous results are available. But let's just consider bounding the degree for now. But this is not the only issue. Another issue that arises regards base change and twists. So the problem is, well, this is not a problem, it's a very nice property, but it does make it more delicate to understand finiteness, is that the property of being heavenly is preserved under base change. So if I take an example of an elliptic curve over Q, for example, which is heavenly, and I base change it up to a extension of degree d, the resulting elliptic curve is automatically heavenly without any additional work. And there's even a slightly more subtle issue going on here, because it could happen that you have an elliptic curve over Q whose base change to K is only is not isomorphic to an existing heavenly curve, but in fact isomorphic to it up to a twist. And that makes it very delicate to count in an accurate way how often these heavenly elliptic curves are occurring. And for now, I'll give a more delicate solution a little bit later, but for now, the solution is to simply count Q bar isomorphism classes instead of isomorphism classes over K. This is a little bit overkill, and I hope I can say something more about that near the end of the talk. But basically, of course, if we only consider things up to Q bar isomorphism, it's not going to be the case that issues of base extension or quadratic twist are going to interfere with how we count these classes of heavenly elliptic curves. Okay. All right. So towards some new results, let me make some related definitions. So first, analogous to the set HKGL, we'll define this coarser set H bar, which simply tracks Q bar isomorphism classes for heavenly abelian varieties. And so there's, of course, an obvious surjection from HKGL to H bar KGL, where we simply pass to the Q bar isomorphism class. And then slightly more delicately, we'll make the following construction. H bar sub F of DGL. Well, what I'm going to do is I'm going to fix one field F, let K run over extensions of degree at most D of that field F, and take the union of all of these isomorphism classes inside of H bar KGL as K runs over these extensions. Then Cam and I were able to show, again with L fixed now, but otherwise letting K run over this family of extensions of bounded degree, we should still expect a finiteness result, right? So in particular, this is not limited to quadratic fields. We can take any fixed bound we want, and we can even take any base field, not just Q that we want. Once L is sufficiently large, we're guaranteed that over this bounded degree family, we will see only finitely many instances of heavenly elliptic curves up to Q bar isomorphism, right? So the same Q bar isomorphism could be represented over many different number fields of bounded degree, but up to Q bar isomorphism, there is a finiteness result. And this is completely explicit, meaning that if we specialize to the case of elliptic curves over a quadratic field, we get a finiteness result as soon as L is not tiny. As soon as L is 7 or larger, we're guaranteed that over all quadratic number fields, we'll see only finitely many heavenly elliptic curves at that particular prime L. Okay, well, as soon as you have a result like this, you should ask, is it possible to do better? And the answer is almost certainly probably not. The problem is that what's really going on is we're really looking at points on some appropriately chosen modular curve, and when L is tiny, that modular curve turns out to be genus 0, and so there's a large number of examples available. And so, for example, this is completely explicit. In an old paper with Akio, we showed an infinite family inside of HQ212. And although we have not written down the details, it's very likely that you can play a similar game at the primes 3 and 5 by simply parametrizing a certain family of points on either y13 or y15, respectively. So in some sense, L equals 7 is certainly the best we can hope for in terms of finiteness results. Well, Let me say a little bit about how we actually go about proving this result. And the idea is to appeal to Levin's generalization of Siegel's classic theorem, on integral points. So if we look at the modular curve y1L, we can define for any choice of D and any finite set of primes S, a set I consisting of just the degree at most D S integral points on this modular. And so in particular, because of the moduli interpretation, we have a good understanding of what an S integral point would be on this modular curve, right? So for example, if I take S to just be the prime L, then S integral points on y1 of L are going to correspond to elliptic curves, which have good reduction away from L and possess a rational L isogeny. And that is essentially exactly the constraints we would need in order to have a heavenly elliptic curve. We have to make sure that the resulting Galois representation really does imply the heavenly property, but this is the case here. And then this is the powerful result that Levin has from the late 2000s, generalizing work of Courvage-Azanier when D equals 2 and the classic result of Siegel when D equals 1, which simply says if you look at degree at most D S integral points on a curve missing sufficiently many points, we're guaranteed to have a finiteness result. Right? And so by using the moduli interpretation and this theorem of Levin's, we're able to basically identify the things we care about, namely heavenly elliptic curves, heavenly at L over some field of bounded degree over some fixed field F. I can just view this as a subset of this set ISD, which is guaranteed to be finite by Levin's theorem. And so as long as we make sure that the identification is truly injective, which is completely standard, then this gives us the finiteness result we're claiming. We do have to note, unfortunately, this is not an effective argument, right? There's nothing about this process, as far as I understand, that would let us say, compute the last L for which you can be heavenly in this case. But it is still a finiteness result that's extremely robust. As long as you have a non-tiny prime L, you can let the field of definition vary up to any specific degree over any specific ground field, and there will still only ever be finally many heavenly elliptic curves of that form.
Can I
Yeah, please.
Are there any values of D and L for which you know that set precisely?
Yes. D equals 1 and F equals Q. Oh, no, I'm sorry. Excuse me. Yeah, I see. No, here in this case, what can I say? No, I don't think so. Even if I take F equals Q, I cannot say for certain about the set 2, 1L. However, if I include the assumption of complex multiplication, I can give this set for every L when D equals 2. And in fact, we strongly suspect that this essentially tells the entire story, except possibly at very small primes. So I'll say a little bit more about this a little bit later in the talk, but essentially, we strongly suspect that once L gets sufficiently large, this heavenly condition has to actually require complex multiplication in the elliptic curve case. We do not have a proof of this, but we have some pretty convincing evidence, I believe, which I'll share with you in a moment. And so for L sufficiently large, I believe we have found it explicitly, but I can't say for certain that we have.
Thank you.
Yeah, thank you. All right. Well, so we have this result where we fix K and let L vary, and there are finiteness results available. We can fix instead L and let K vary in some controlled fashion, and we have finiteness results available. And so we could just shoot for the stars. We could ask whether or not letting both L and K vary in some presumably controlled manner might also lead to finiteness results. This is a naive hope, so it's going to require some adjustments. First of all, we've already observed infinite families when L is less than 7, so there's no hope of getting a finiteness result if we don't account for that. There's also issues around base change constructions, which have to be accounted for. And okay, we can play the same game by looking at cubar isomorphism classes, but it's not immediately obvious that solves all the problems that it solved before. There's a subtlety which is that if I fix one particular elliptic curve over Q, just with good reduction away from L, not necessarily heavenly on its own, possibly it could have many base changes over quadratic fields that pick up the heavenly property, because of course, whenever you base change by a field where a prime you don't like ramifies, you can get the bad reduction to sometimes drop out. And so it might suddenly be the case that there's this infinite supply of examples lurking, coming not just from elliptic curves that were heavenly over Q, but just elliptic curves that had good reduction over Q, for example. And this is actually exacerbated in ways that are sort of annoying to spell out in detail when you start thinking about isomorphism classes up to quadratic twist, because it could potentially happen that you have an elliptic curve over Q that base changes to something over a number field K, quadratic field K, which is not yet isomorphic to a class you have, but that becomes isomorphic upon looking at quadratic twists. So over some further extension, an isomorphism becomes available. So whatever finiteness results we might hope for in this direction, we have to try and do some careful accounting or grounding these things. But let's try anyway. Let's see what we can say. So I'm going to define a different set, H circle. So this circle I'm thinking of as open, deleting a small number of cases as I build this set. I'm going to let L be prime greater than equals 7 and assume K is always a quadratic field, field degree 2. Take A over K heavenly at L. And I'm going to make the following assumption that there's nothing over Q already heavenly that's in the same Q-bar isomorphism class as the elliptic curve A. Right? So we look at all the pairs that meet these conditions, heavenly over the base field that's a quadratic extension of Q, but not in one of the finitely many Q-bar isomorphism classes represented by something that is heavenly over Q already. This is a very minor restriction, this last bullet point. We know the set HQ1 explicitly. It spans only 16J invariants, so we'd have to avoid. And moreover, we're talking about pairs here. So in fact, for any particular L, I'm not actually restricting 16J invariants. I'm restricting maybe 2 or 3, depending on what the prime is. And so this is a very mild third condition to add to the set H circle here. But what it does is it helps us eliminate nonsense coming from base change and twist constructions. All right, we conjecture that this set is finite. And that's a little bit bold because I haven't given enough of a justification for this, but I'll come to that in a moment. But it can be a little bit difficult to wrap our mind around this set of pairs of curves together with primes at which they're heavenly. So I'd like to present a different sounding finiteness conjecture, which turns out to be equivalent. So rather than asking to tabulate all of the elliptic curves which are heavenly over some quadratic number field, we can instead ask this as sort of a binary yes-no question. If I pick a quadratic number field K and a particular prime L, do I expect there to be any heavenly elliptic curves at that prime L over that number field, not already represented by something that was heavenly over Q? So this final bullet point is the same restriction essentially that I put on the set H naught on the previous slide. And now, instead of asking to sort of tabulate all the individual isomorphism classes, we're just asking yes or no questions. If I give you a prime L and a number field K, quadratic number field K, are there interesting new examples over that number field at that prime L or not? And I'm going to make this perspective even just a little bit coarser. So let's make the following observations. First of all, if I fix the quadratic number field K and the prime L, I'm at least demanding good reduction away from L. And so by the Shaffer-Avich conjecture, I'm only going to have finitely many examples of this. And then, at least in the quadratic case, of course, anytime the degree is fixed, specifying the discriminant or even the absolute value of the discriminant of the number field restricts you to finitely many cases. So we conjecture that this set R is finite. And in fact, the finiteness of R and the finiteness of H naught, those are open problems, but those are in fact the same question. This is something Cam and I were able to establish earlier this year. And there's a little bit of content to this because you have to show that it's impossible for some J invariant to be represented by infinitely many quadratic number fields and not be represented over Q. So that turns out to never be possible, and that's what needs to be shown in order to give the equivalence between these two finiteness conjectures. Okay. All right. So the conjecture is open. Could these possibly be finite? But either phrasing of this conjecture turns out to be equivalent. They are, in fact, the same question in disguise. That's still not really a convincing argument that we should expect these sets to be finite. So let's try and give some understanding as to why to expect this. So first of all, the advantage of building this set R as a subset of pairs of natural numbers is because we can finally sort of concretely visualize this set. So the set R has an x coordinate indexed by some prime L, and some y coordinate indexed by the absolute value of the discriminant of the quadratic number field. And we can sort of think of R as a set of points distributed inside of n cross n. And a lot of what's already known hints at some sort of finiteness. So first of all, the old results that I have with Akio are basically saying that the horizontal fibers of this set R are finite. That is, if I fix the discriminant of a number field, i.e. restrict K to one of a finite number of choices, and move left to right along this horizontal fiber, I should see only finitely many points that exist inside of the set R. And another way to think of that is that there's just some bounding curve off to the right here that completely forbids elements of R to lie beyond this curve to the right. And the more recent result that Cam and I have established is essentially a vertical finiteness result. If instead we pick one particular prime and try and look for examples of heavenly elliptic curves at some quadratic number field over that prime, again, there are only going to be finitely many such instances allowable. And this is essentially equivalent to saying that there's some curve that bounds this set R from above. Unfortunately, there's absolutely no guarantee that the curves I'm describing ever overlap. So this does not resolve the conjecture of finiteness at all, because it may be that infinitely many pairs manage to escape off in this direction in the gap between two curves. But if we sort of account for everything else, we can give some more evidence here. Right? So we'll ignore the fact that at tiny primes we have infinitely many classes, and observe a couple other results that already exist. First of all, Abby in her thesis gave
ask a question?
Yes, please.
So when you say this is a curve, I mean, do you know that it's like continuous or like any?
No, of course not. So I'm being a little bit tongue in cheek, right? There is a, for example, so here, when we say there's a curve, of course, what we mean is that for each individual number field K, there is some last L. And so you can imagine these sort of forming some sort of boundary to the right. Yes. So I am using curve euphemistically here. I'm not claiming that there's some bound that I can describe in a reasonable way. I will modify that slightly. The top picture is definitely not describable by a curve by current technologies, because remember, these vertical finiteness results are ineffective, right? So I don't know how to describe the growth of the last discriminant as I consider vertical fibers. If you grant GRH and look at horizontal finiteness, then the situation is actually easier. You really can describe the growth of sort of the last prime that's possible. This is still sort of a weak result, because then computationally under GRH, you can drastically improve the bound. So I've drawn this curve this way here, but in reality, and I'll say a little bit about this at the very end of my talk, in reality, this curve is probably the line L equals 163. We know it is up to some fixed discriminant. We've verified this under GRH. The technique for proving such a thing is actually quite standard. It's not computationally intensive as long as you give yourself GRH. But the problem is it is field specific. So there's no way to extend this into a uniform result. All you can do is calculate, you can sort of turn a computational argument into a proof, one quadratic field at a time. Right? So again, just to recap, I think at least under GRH, there is some sort of curve behavior that can be described. Here, there's just some bound from above. There's nothing we can really say about the shape of this bound like we can in the other case. Is it a satisfactory response, or is there more I can say?
Yeah, sounds great. Thanks.
Okay, great, thank you. All right. Okay, so now let me talk about these two bullet points here, because this is where the potential finite result really seems to start to come into focus. So again, in Abby's thesis, she demonstrated not just finiteness results in the CM case, but a uniform bound on the prime when you assume both heavenly and CM. And so the takeaway from that is that to the right of this second dotted line I've labeled CM, all the heavenly examples have to be non-CM. They are not allowed to have complex multiplication. That is a theorem of Abby's. On the other hand, Cam and I, when we were studying heavenly elliptic curves and abelian varieties more generally, we found this property that I'll explain in more detail in just a moment, which I'm calling balanced. It has to do with the structure of the L torsion as a group scheme. That has to be satisfied uniformly just based on the prime alone. So essentially, there's some structural component to being a heavenly abelian variety that cannot survive unusual behavior when L is large. And so this condition, which I'll define in a moment, has to hold for any elliptic curve that's heavenly and has L larger than 19. So we've got this boundary from Abby that says everything to the right of the right line does not have CM. Everything to the right of this first line marked balance has to be balanced, excuse me, and there's overwhelming circumstantial evidence to suggest that balanced requires complex multiplication. So I'll make that more precise in a moment, but of course, that makes this dark blue region very difficult to populate, because anything in this region, if it does turn out that balance does imply complex multiplication, has to simultaneously have potential CM and not have potential CM, which is of course impossible. And so if we could turn this evidence into a theorem, that would actually give us the strongest possible finiteness result where we let both L and K vary. All right. So bold claims require bold evidence. So I will try and explain why I believe there's significant evidence for this and how we might go about investigating it further. So I have to think a little bit more carefully about the structure of abelian varieties here to describe the next condition. So let's suppose we have a number field K, and we pick a rational prime L, and I'll take some prime of K over L. And let's assume A is a heavenly abelian variety right now, heavenly at L over K. You can tell the story I'm about to tell if L happens to ramify in K, but for simplicity, let me just assume L is ramified. Then we can look at the following tower of local fields. I'll first take the maximal unramified extension. Then, as is well known, there's a finite extension over which A is going to obtain semi-stable reduction. And then on this subgroup of the inertia group, which I'm calling JL, defined by this semi-stable extension, there is a construction known as the fundamental character. So how does this work? Well, if we take a uniformizer inside the ring of integers of the field over which we obtain semi-stable reduction, we can go grab an L minus first root of that uniformizer and then determine how Galois elements chosen from inside of J move that L minus first root of the uniformizer around. In particular, if I look at that root and hit it with sigma and then divide by the root without Galois action, this is going to pluck out a L minus first root of unity, which of course is just a copy of FL cross in disguise. And so we get this construction called the fundamental character that gives a one-dimensional representation of this subgroup of the inertia group into FL cross. And it's a classic result of Serre that says we actually know quite a bit about the interaction between this fundamental character and the cyclotomic character. If you restrict the cyclotomic character down to JL, then the cyclotomic character is exactly given by the ETH power, E being this degree of semi-stable reduction here, index of semi-stable reduction. The ETH power of this fundamental character gives us chi. And that's as far as the story goes if we don't add in the heavenly assumption. But with the heavenly assumption, there's suddenly a lot of simultaneous constraints being put on the L torsion of the abelian variety. So the characters associated to components of the L torsion as a group scheme were studied by Tate and Oort. And essentially, some decomposition, essentially the semi-simplification, has the following property, that there are small powers, these integers JR, are chosen between 0 and E, such that on the semi-simplification, you get these powers of the fundamental character marching down the diagonal. And in the case that A is heavenly, we already have the diagonal expressed to us in terms of these cyclotomic characters. And now suddenly we have two simultaneous constraints relating the fundamental character and the cyclotomic character. We have the eth power constraint coming from Serre, and now we have these additional constraints that certain powers of the fundamental character must line up with certain powers of the cyclotomic character. And that's sort of too much to allow the J's to be chosen freely. They're suddenly under a lot of pressure. One thing that you can observe right away is that these numbers, these JRs, coming from the powers of the fundamental character, sort of pair off into G distinct pairs, each of which sum to E. And of course, the most symmetric way you might have this happen is if every last index turned out to be E over 2. So if every single power of the cyclotomic character appearing in this representation happens to be E over 2, that's what we're going to call balanced. Okay. And Cam and I were able to study this in terms of the constraints placed on it by the, the two different shapes of the Gauss representation. And if you start dropping Frobenius elements at larger and larger primes into this picture, demanding that the abelian variety is not balanced, you can generate contradictions to the V-bound. And so as a result, we were able to prove this in complete generality, that if you fix a dimension and a degree n, then an abelian variety of dimension g over a field of degree n eventually has to be balanced with respect to a uniform bound. So there's a constant depending only on the degree of k and the dimension of a, past which the abelian variety has to be balanced. And this is completely explicit. Depending on how hard you're willing to work ruling out cases, you can compute a very precise bound, not necessarily sharp, but incredibly close to sharp, for any specific choice of n and g. We've done this in a couple of cases. And the one I care about right now is, the quadratic case for elliptic curves. It turns out this bound is only 19. So if L is bigger than 19, a heavenly elliptic curve has to be balanced. Okay. The proof is actually relatively technical, but it does build on this general strategy. The whole strategy is, if you're not balanced and you're working with a large prime, you're going to be able to find some Frobenius element that violates the V-bound, and that's where the control comes from. Okay. All right. So let me explain where the interest in this condition of being balanced comes from. I want to compare the behavior of heavenly elliptic curves which are balanced versus elliptic curves which possess complex multiplication. And so everything I'm going to say right now is over a quadratic number field K. And I'll make some starting assumptions. I'm going to take an odd prime, take a prime of K that doesn't divide L. And I'm going to look at the Frobenius of that prime and consider its trace AP. And for simplicity, let me fix a field L to be Q root minus L. The results that are known both classically and for us are slightly more general, but for simplicity, let's just take this case. And we have the following phenomenon. Let's first talk about what's known classically for curves with complex multiplication. If I have complex multiplication by the maximal order, and I have good reduction away from this one prime L, then the splitting behavior of primes over K in the compositum between K and the CM field is tied very closely to the trace of Frobenius. So when the prime splits, you get this congruence satisfied by the trace of Frobenius. AP squared has to be 4 times the norm of P. And if P is inert, we actually get the very famous result that the trace is exactly 0. Okay. And I want to compare this instead to heavenly balanced curves instead. So instead, let's suppose E over K is heavenly at L and balanced for at least one of the primes dividing the rational prime L. Then we're again able to demonstrate splitting behavior dictating the trace of Frobenius in the following way. If P splits, we get the exact same congruence as in the CM case. And if P is inert, we do not necessarily get 0. We were only able to prove that you get 0 modulo L. But this is still pretty striking behavior for curves that a priori might not have complex multiplication. There's a subtlety that I couldn't think of a way to spell out clearly on a slide, so I'd just like to talk through it briefly. In the classical case, it's known how to find which square root AP is. So that is, you get this congruence, and then there's a character that will spit out the appropriate sign of the trace of Frobenius. And something similar happens in our case, and it's actually more explicit. We're able to more quickly explain how to choose the sign to recover the trace of Frobenius, as opposed to just its square in the splitting case. And that makes parts of the argument a little bit easier and more explicit. Okay. All right. There's an idea that one might have when you see this data, and that is that surely there's a contradiction available through Sato-Tate, and unfortunately this is not quite true. The congruence mod L instead of an actual equality gives just enough room for the distribution of traces to avoid violating Sato-Tate. I mean, it's still incredibly unlikely behavior in some philosophical sense, but we can't use it as a quick argument to say a non-CM curve cannot possibly be balanced for sufficiently large L. However, the result that we proved, tying the splitting behavior to the trace of Frobenius mod L, was actually enough for us to establish a characterization of the following form. Among all elliptic curves, the complex multiplication defined over a quadratic number field, some of them have good reduction away from 1 prime. And among those, some of them are heavenly, and we can identify them. So the condition turns out to be very explicit and natural. All you have to do is look at the trace of the L torsion representation. If you do not get full trace, that is what implies an elliptic curve is heavenly. This is actually if and only if, under the starting assumptions that E has complex multiplication and that the field of definition is minimal. That is, we have to assume that K is exactly the field Q adjoining the J invariant of the elliptic curve. The result is actually even more striking than that. The image of trace we can describe in the exceptional case quite easily. It's essentially half of FL. You either get 0 and all the squares, or you get 0 and all the non-squares, and this is entirely determined by the Lysander symbol of 2 over L. And as long as L is not tiny, we can even demonstrate that the elliptic curve has to be balanced at every prime dividing L. Okay. So this does not lead to a finiteness result because, again, there may, in theory, be elliptic curves over quadratic number fields which are heavenly but don't possess complex multiplication. But barring that, this gives us a method for completely tracking down all of the balanced elliptic curves with CM, right? So we did this. We took this computation as follows. So we found a collection of pairs, E comma L, where E is defined over the quadratic field generated by its J invariance. It has complex multiplication and satisfies the heavenly condition. Now I'm wording this slightly carefully. This is a finite set that contains all such pairs, but it, in theory, might have some pairs that don't involve E being heavenly. So why is that? Well, I can't compute the entire image of the Galois representation on L torsion on all Frobenius elements, right? There are infinitely many Frobenius elements. But I can take a large subset of them, right? So I can take the first 20,000 Frobenius elements and compute the trace of Frobenius. And if I get more than half of possible traces, then I immediately know we're not heavenly. And if somehow over 25,000 coin flips, I still have not gotten too many traces, I strongly suspect that the elliptic curve is heavenly. Okay. And so we may have some false positives, but this seems extremely unlikely. And I will mention a couple of things we noticed when we did this calculation. One is that we did find an isogeny class of elliptic curves that managed to be heavenly at 2 distinct primes simultaneously, and this was certainly a first. We did not have a single example of this behavior anywhere prior to this discovery. And then I'll just mention one more closing remark, which is that we did go back and look at what we could say under the extended Riemann hypothesis. Of course, under ERH, for example, there are explicit bounds given by Bach and Sorensen for determining the first Frobenius that lies in your favorite conjugacy class of the Galois group. And so we were able to use that to find a reasonable bound past which L could not possibly be heavenly, for which an elliptic curve could not possibly be heavenly at L, and then manually just check all the primes between 163 and that bound, which would say be on the order of 50,000 or something, to get a Riemann hypothesis-dependent proof that 163 was a bound on heavenly curves over that field, CM or no. And we were able to carry out that calculation out to about 500,000, discriminants of size 500,000. Okay. Yeah, I think that's probably where I'd like to stop. And I'd like to thank you again for letting me have the hour.
Great, thanks, Chris. Well, we've had some nice questions so far. Are there any more?
Do you have any results for abelian surfaces? I mean, specifically rather than general bounds?
We know AQ1 is finite. I have an perennially unpublished, but someday result with Akio that under GRH, 163 is also the bound for abelian surfaces over Q. Actually, the proof is relatively easy to describe, even though, of course, there are tons of details to check. We understand the moduli space A2 well enough to just consider the three possibilities. You're a pair of elliptic curves, or you're a simple Jacobian, and you just consider both cases and come up with an argument very similar in spirit, actually, to this trace of Frobenius argument that is running under some of the things I've talked about here. But in larger dimensions beyond that, or different number fields in Q, I don't think we have a single finiteness result. There's an example constructed by David Lombardo that's heavenly at the prime 61. That's an abelian surface. I think that might be the only other explicit example I can think of off the top of my head.
And do we know of any balanced abelian varieties of any dimension that are not heavenly, or sorry, that are not CM?
Yes, what an excellent question. So at 2, right, there's this infinite family that passes through infinitely many J invariants. So there's definitely some there. Okay, so then we politely scoff and then ask for other examples, and the answer is no. If we sit down and come up with the infinite families at 3 or 5, probably we can also come up with non-same examples there. Over Q, there is a non-balanced elliptic curve with L equals 11. And that is it. That is what I know for non-CM. Tiny primes, L equals 11 over Q. I do not have a single non-CM example with large L that I can report on, even though we found all of the CM examples over any quadratic field.
Well, a target for people to shoot for then.
Yes, please do.
Great, Chris, thanks again. And let's thank Chris again. And our next talks are on May 20th at the unusual times of 9 a.m. and 10 a.m. Eastern Time.